Welcome everyone to this webinar. I think that we will start now. It's a few minutes past 3, so we can start and the rest will join later. So I'll just introduce myself. My name is Jonathan Claymark. I work for Camsec and I am the project manager for the Pfas Movement project that we have that we will talk very briefly about today, among other things. I will start with some practical things. If you have questions for the panelists, please write them in the Q&A function. And we will have a Q&A session in the end of the webinar where we'll answer as many questions as we can. We will provide the slides after the webinar, and we will also record this webinar if you're interested in seeing it again, or then if there is someone who's missed this that want to see it afterwards. So I will start by giving a very brief introduction to Camsec, and my colleague Josephine will talk about Pfas Movement, and then Gunnar, our expert regarding tests from IVL, will talk about the specific testing for Pfas that is the focus for this webinar. But a short agenda. As I said, we will talk about Camsec and also about Pfas, what kind of substances they are, Pfas Movement, and the testing part. And we will end with the Q&A session, and we hope that we will have quite some time for that session if there are many questions. And if we are not able to answer your questions during the Q&A, we will save all the questions. So if there is any specific interesting question that you have, we will come back to you regarding that. So please feel free to ask as many questions as you want to. So just briefly about Camsec, for those who don't know who we are. We are an environmental NGO based in Sweden, and we are working towards reducing the use of hazardous substances. We work together with different stakeholders in order to drive the change to safer chemicals, and we are funded from both the Swedish government, but also from various charity funds. And I should say or stress that we don't get any funding from the companies that we work together with. We try to work with no name and shame. Instead, we try to highlight the progressive businesses and how successful it can be to be progressive regarding chemicals management. We work in some different ways. We work with policy, influencing policymakers. We work a lot with different businesses, companies, engaging with them, understanding the challenges of chemicals management and how we can support and what is a good legislation for them. We work with investors to help them understand the hazards of hazardous chemicals. And we also have a set of online tools for companies to use. Some of them you might know. The most famous one is probably the SIN list, which is our list of hazardous chemicals that we think should be banned. Similarity is our tool for identifying structurally similar chemicals to avoid regrettable substitution. Marketplace is our online platform for safer alternatives to hazardous chemicals. And ChemScore is our ranking tool where we rank chemical producers. So that was brief about Camsec. If you have any specific questions on Camsec, please, you can add them to the Q&A as well. Just now, some slides regarding Pfas, which is the focus. So Pfas stands for pair and polyfluoroalkyl substances. And it's a very diverse, very large family of substances. There are different ways of estimating how many substances there are. Some say it's around 5,000, some say even 8,000 or 9,000 different substances. But they have several very valuable functions. They are, for example, water and oil repellency, non-stick, and they are very inert to outer influence, which is a very good function in many situations. But they are also very persistent and mobile. Persistent meaning that they do not degrade. They are in many cases bioaccumulative and toxic. And I have also added an example of how structure can look. This is the PFOA, which might be the most famous of the PFAS substances. They are known to have many different health effects, like cancerogenics. They have causing liver damages. They have endocrine disrupting properties. They did reduce antibody effect, which is now very interesting because it means that the vaccines can have less effect. They are also, since they are so very persistent, they are and mobile. This means that there is a lot of water contamination of PFAS. Because since they are very persistent, do not degrade, they will, and mobile, they will end up in water and stay in water for a very long time, meaning that we can drink a lot of PFAS. There is a lot of PFAS contamination in water sources around the world. So just a brief slide regarding the functions. As I said before, there is a very large array of functions and uses of PFAS. There was an article late last year regarding the different uses where they had identified over 200 different uses. I think that Gunnar will talk a bit more about this in his presentation. Some example from consumer products are the textiles and shoes, for example, Gore-Tex, frying pans, where the non-sticks are usually Teflon, which is PFAS, and food packaging, for example, in fast food, where we can wrap hamburgers and other French fries, for example. But there are also many other more industrial examples of the functions, especially in the fluoropolymer production, but also lubricants, surface treatments. They're used in electronics, for example, in cables, coatings and paints. They are basically used everywhere, meaning that it's also a big problem since they are so persistent. It has been a lot of focus on PFAS legislation-wise lately. PFOA and connected substances were restricted last year. And in the chemical strategy that came October last year, PFAS is mentioned as a substance of family that should be banned, except for when it's an essential use for society. There is also work of compiling a broad PFAS restriction. It's 5 countries in EU, Sweden, Norway, Denmark, Netherlands, and Germany, I think, working to do that, where the aim is to have a restriction done in 2024 or 2025, which is quite soon. But there are also specific countries that have specific legislation. For example, in Denmark, food contact paper and board, where PFAS is banned. Some research, there is a lot of research going on. For example, what is the definition of essential use? Can we map the different functions and uses for PFAS? Persistence, is that sufficient for classification and for making it an SVHC, for example? But also regarding the antibody effect, vaccine efficiency. We have also seen that people that's been affected by PFAS has a higher risk of having a severe COVID-19 impact. And all of this, since the PFAS is present in so many different products and the increased focus, in combination with a lot of new legislation that's in preparation, means that many companies need to take action regarding PFAS. And especially it's interesting to understand how a company or an organization can find, where we can find PFAS, how you can find it, how do you test for 5,000 substances in order to find conformity of saying that you don't have PFAS, for example, but also identification of the presence and what kind of PFAS you have in the different product. And this is something that Gunnar will talk more about in his presentation. And now I will leave to my colleague Josephine, who will briefly introduce the Pfas movement.
Yes, so Pfas Movement, it's our corporate Pfas movement that we founded in 2020. And the aim of this was to influence PFAS restriction and to facilitate kind of a network of companies that want to work with PFAS. So basically, we use the input we get from companies in our discussions with policymakers, and by collaborations within the movement, we find solutions connected to PFAS challenges. So our focus has mostly been on Swedish companies, but we're now expanding to the EU and US. You can change the slide. Yeah, so these are the companies, some of the companies that are in the PFAS movement as of now. You can change the slide again. So what it implies to join, there's no need to be to have phased out PFAS from your products. Some companies that we work with have still have PFAS in their products, and other just started their journey, and some phased it out years ago. To join our initiative means that you support a stronger PFAS regulation, and that you support that PFAS substances are targeted as a group. You encourage the chemical industry to develop safer alternatives, and you publicly state that you have the ambition to phase out PFAS from products and supply chains. The level of ambition is up to you as a company to decide. We don't do any follow-up controls on what you've done, but rather we expect that you investigate the presence of PFAS in your products, and that you communicate with suppliers and understand how it can be phased out. Next slide. Yeah, so what's in it for you as a company? Well, first of all, most importantly, you'll receive information and advice before facing possible consequences from regulations. You'll also receive assistance throughout the journey of working on the issue of PFAS. We can help you with discussions with suppliers and finding alternatives, etc. You can use it for sustainability reports as an internal and external communication tool and opportunity. And you also get the chance to communicate and connect with other companies regarding challenges and opportunities connected to PFAS. And there's also the opportunity to be uplifted as a role model towards other companies and policymakers. So that was it about our PFAS movement. And now I'll hand over to you, Gunnar, that'll tell us more about PFAS testing.
Okay, thank you very much, Josephine and Jonathan. Okay, my name is Gunnar Thorsén. I'm Associate Professor in Analytical Chemistry at Stockholm University, but I work at IVL. And at IVL, I am the head of the environmental chemistry group that we have. At IVL, we do a lot of chemical analysis in many different environmentally relevant matrices. Everything from water samples to products and to sewage sludge, and even different types of biological samples that we analyze. Next slide, please. Like Jonathan said, PFAS is a very large group of compounds. More than 4,500 compounds that the OECD lists in their list. And like Jonathan said, very persistent, and that is the major concern of these, or one of the major concerns, because if we want to get rid of them, we probably need to sort of destroy them in the end. And it's very important to not release new ones into the environment. This is a picture I've taken from the publication by Glüge et al. That came out earlier this year, and which lists a lot of different uses of PFAS compounds. And here you see just a subset of the many different chemical structures that PFAS compounds can have. So it's a very diverse group of chemicals. And so they can have anionic, cationic, zwitterionic, zwitterionic meaning that they can be positive or negatively charged depending on the pH, and non-ionic. So they have many different types of, they express different properties. Next slide, please. And this is from the same paper, this picture. It shows the applications taken from the SPIN database that between 2007 and 2017, or 2010 to 2017, I think, and it shows many different uses, and it shows also that demonstrate that polymeric PFASs are quite often used rather than just monomeric PFASs. Polymeric PFASs meaning that there's a chemical backbone of some structure to which there are a lot of classical PFAS compounds linked. So many uses, and quite often polymeric PFASs are used. Even though that is the case, most of the analysis that has been performed on PFASs have been performed on either PFOS, PFOA, or a subset of the number of chemicals called PFAS 11, which were recommended by the Swedish Food Agency for measuring in water samples, in drinking water samples. You can please jump to the next slide. So what I'm going to talk or present today is the chemical analysis of PFAS. When you say PFAS testing, you may also think about testing, toxic testing or toxicity testing or those kinds of testings. But I'm only going to talk about the chemical analysis and how much of the compounds you can find in your sample or a specific sample. Now, the most common way of analyzing PFAS or measuring PFAS is by using the liquid chromatography coupled with mass spectrometry detection, LCMS or LCMS, usually denoted as. And this is a target analysis method where you measure specific PFASs. Other PFAS testing that has been common that have been commonly presented in the literature are the total oxidizable precursors. I will come back to that one later in my talk. It sort of determines which PFASs that can be created from precursors, from polymeric substances that may be present in the samples. There's also two sort of testing techniques that I won't speak about today, and that is the total fluorine analysis using instrumental methods such as particle-induced gamma ray emission. That is a sort of a technique where you bombard your sample with protons or neutrons, and then you get an emission of gamma rays, and there you can see the total fluorine content. It's even non-destructible as a testing tool, but you won't differentiate from PFAS compounds or from compounds that are organic compounds with fluorine in them, or if it's inorganic fluorine that you're seeing. I will, however, talk about the next one that I have listed, the adsorbed or extractable organic fluorine. And there, what you do is essentially you extract perfluorinated and polyfluorinated compounds, even if they're precursors or polymeric types, and then you measure them with combustion ion chromatography. And this I will explain more in detail. Now, the very large number of PFAS compounds and the awareness that these are out in the environment around us comes from the suspect and non-target screening, which is performed using high-resolution mass spectrometry instruments, and where you get you get the weight of the compound, and then you can do some database searches or mass spectral comparisons, and you can make a tentative identification of a specific perfluorinated molecule And that's the way that you can determine very, very many of these. But you rarely get a quantitative answer using that. And I won't talk about that because that's like a whole seminar in itself. Next slide, please. So why is this important? Well, this is a picture I've taken from a paper by Laura Schultz at ACES. She's now at Harvard, which we collaborated at IVL in this paper. It presents the fluorine, organic fluorine content, or the fluorine content in cosmetic products. They bought cosmetic products which were supposed to contain perfluorinated compounds or fluorine compounds. And here we see that if you look at the blue bars, that's what is determined using the target methods, where we're looking for specific PFASs. The red bars are the ones are determined using the extractable organic fluorine. So that's all the organic fluorine compounds that are sort of extracted from the compound, from the sample. And the yellow bars are where they've taken the sample in itself and combusted it and measured it using combustion ion chromatography. So you see, in this case, there's a large number of fluorinated compounds that we do not measure using the specific analysis methods. And this is more and more coming to light that this is the case. Now, I'm not saying that it's not worth to make the specific analysis, but these analysis methods give you different information. Next slide, please. So if we look at the sort of chemical tests that are routinely done, or that have most been done, it's been done with target methods using LC-MS. And there are many suppliers. There are several labs that actually sell these types of tests. We are one, but you can also find quite large panels of PFAS compounds also from Eurofins or from ALS or from Synlab, for instance. So the big commercial environmental labs also perform these types of tests. They can also perform the top assay, for instance. But here we see that on the left side, we see the 11 PFAS that are recommended by the Swedish Food Agency. And on the right side, we see the 20 PFAS compounds that is suggested to be monitored in drinking water in upcoming time. And these chemicals are they are predominantly of the carboxylic acid type or the sulfonic acid type. You don't see very many other ones being suggested in this, but we know that they are present in consumer products and in a lot of different samples. And they have been seen for about 10 years in the environmental samples. So next slide, please. So how does a normal LC-MS analysis work? Well, the analysis is based on partitioning. You separate the compounds on by differential partitioning between a stationary phase and a mobile phase on the HPLC column that is in the sort of center of the picture. Then the compounds come to the mass spectrometer, where they are converted to ions in the ion source. And then the MS instruments, or the mass spectrometer, gets a signal which is very specific for each PFAS. The usual thing to do is to use tandem mass spectrometry, where you have 3 mass filters, quadrupole mass filters in a row, where you, in the first one, select one ion the mother ion, which is the PFAS compound that you want to analyze. Then you break this one down in a collision cell, and then you measure 2 ions that are formed. So you have one quantifier ion that you calculate your quantity based on, and one qualifier that certifies that this is the chemical compounds that you're trying to measure, because you can relate it back to that a reference standard behaves in the same way. It has the same retention time and it has the same fragmentation pattern. Now, it's a very selective measurement technique. It gives very low detection limits, but it's depending on that we have these reference standards compounds available. And that's very difficult for such a big group of chemicals. You also would like to have isotopically labeled internal standards to make the quantification easier. And that's not always readily available either. So that's a bit of a hassle for the labs. Now, what we have to keep in mind is that this is a technique that is very good at finding the needle in the haystack. So if you just click on the forward in the presentation, you see the needle, but you may miss the bike or the hammer that is also in the haystack, because it's such a selective analytical tool. It's very robust, and there are established techniques available. So next slide, please. So moving on to the AOF or the EOF, the extractable organic or extracted organic fluorine, or the adsorbed organic fluorine, which is sometimes is referred to. This is an analysis method based on combustion ion chromatography, and either the compounds that you're interested in are adsorbed onto activated carbons, so they are extracted from the sample using particles that are added and then taken care of, or you extract it using organic solvents, and then you get the organic solvents and you introduce them into your instruments. So these are, like in the farthest left of the picture, they're put in a sample boat that is then introduced into an oven. Either the liquids or the solids can be put into this sample boat. It's introduced into the oven where they are controlled. They're combusted in a controlled environment with oxygen, argon mixtures, usually with water content in the gas. So all the sulfonic, the sulfur-containing compounds are converted into sulfate, and all the halogenated compounds are converted into the corresponding halogen ions, like chlorine or fluorine ions. Now, these are collected in a aqueous solution, and then they are injected into an ion chromatograph. So you make the measurement based on how much fluorine ions that are produced during the analysis. Next slide, please. Okay, looking at the third type of analysis that we will touch upon. This one is supplied by several labs. The extracted organic fluorine is more, if you're doing PFAS analysis, you usually need to get in touch with a university that is making these analysis. I don't know if any of the commercial labs have started to sell this analysis yet. But this top assay is not uncommon actually to find. And we also do this type of analysis. So in the top assay, you start with a sample extract that you have PFAS compounds in. You divide it into two, and one of these you make a standard LC-MS analysis making a target analysis of the PFAS compounds that are there. The other sample part, you take and you oxidize what is there under controlled conditions that do not affect the original carboxylic acid PFAS or the sulfonic acid PFAS that were in the sample from the start. So what you're actually changing here is that most polymers and some groups like sulfonates or phosphonates or PAPs and those kinds of PFASs, they will be degraded into the corresponding carboxylic acids. Then you take that sample and you do a new targeted analysis of that. So you will then detect a change to the carboxylic acid PFAS, and you will also look at some changes of the non-carboxylic and non-sulfonic acid types of PFAS. They will also be converted into the carboxylic acid types. And these will then, you compare the samples, you will see if you're able to understand whether this change can be explained by the other target PFASs that were in the sample that you analyzed from the start, or if they originate from precursors, from polymeric PFASs that you did not see, or other types of PFAS that you couldn't have that wasn't in your original target method. So it gives you an information of unknown PFASs and also polymeric PFASs that can break down into these corresponding carboxylic acid types. Some PFASs are resistant to this oxidation, such as the F53B, which is a substitution for sulfonic acid PFASs in several cases. Next slide, please. So if we summarize these three techniques and the sort of merits of these that we have, the target analysis using LCMS, you get the specific determination of compounds that you expect to be there. The top assay determines the corresponding carboxylic acids that are formed from polymer PFASs or that are formed from other PFAS compounds present. So you know you can get an idea of that. And the EOF determines the fluorine content that originates from organic molecules that you've extracted from the sample. So the part of organic fluorine content is increased as you go further to the right in the picture, while the selectivity and the recovery, the certainty of the analysis increases to the left in this picture. It's very difficult to make recovery, or I would say impossible to make extraction recovery determinations of the top assay or the EOF type of analysis, because you don't know what chemical compounds that are actually giving you your signal. So you can't add those compounds to a sample and then evaluate what proportion is extracted. So there's some uncertainties, of course, in these types of analysis. Next slide, please. So looking at the limitations. Now, the target LC-MS analysis, of course, may not cover all the PFAS compound present, because there are usually just a small subset that is available from the target analysis methods. The labs that have most have between around 85 or 100 PFAS compounds that they determine in a single run. And this is much due to the lack of available standards. Also, can be differences between different labs. So if you get the result from one lab, it may not completely overlap with the results from another one. And that is because there's a limitation on the availability of certified reference material available. So it's difficult to make inter-lab comparisons still. Ultra short chain PFASs, usually that's like trifluoroacetic acid, for instance. These have been talked a lot about in recent days. They are usually determined using supercritical fluid chromatography, which is a technique which is similar to LC-MS. There are also methods presented using LC-MS. They are, since TFA is such a common chemical, they are quite prone to contamination. And as they are volatile, many of these, they're prone to losses during workup. And the same is, of course, true for volatile PFAS, where there's another issue that the sensitivity using the LC-MS instrument is not that good. And sometimes you need to look at GC-MS methods to actually get a low enough detection limit for those types, for the fluorotelomere alcohol. For the EOF, well, you only see the things that you have extracted or that you have adsorbed to the carbon. You may get inorganic fluorine that you're not getting rid of, so you're not really certain that it's only the organic fluorine or the potential PFASs that you're seeing. So you're not really certain to get everything in that assay, even though it's probably the one that gives you the most fluorine content. And the top assay are, the limitations are that some of these are stable to this degradation, and the information is not always that super easy to interpret. So I would say, if you're uncertain, then talk to the analytical laboratory that you want to use. So you get the analysis that you want. Next slide, please. Okay, thank you very much. I hope I can have time to answer your questions as well. Here's listed some people that are in IVL that are working with PFAS issues, and you can see sort of what they are working with. They've also helped out with this presentation, also with information, of course.
Thank you very much, Gunnar. We have a few questions, so I will start with them. One question regarding the availability. Are these test methods commercially available at the big test institutes around the world, or are they still more on a research level?
You see some companies, most companies have the target analysis methods, absolutely. And not all of them will do material testing, and not all of them will do testing in fish and stuff like that. But many of them have the target methods, and for quite many compounds. The EOF, the combustion ion chromatography, is not that common to find. The TOP assay, as it is based on the quantitative analysis using the LC-MS, so it's actually using the same instrumental method, but it's just a preparation of the sample that is then often sold by the major suppliers of analysis testing.
Is it possible, this was a question from me actually, is it possible to, I mean, if we're talking about cost for the different testing, if we take the target at the top and the EOF, which is the most expensive, and is it possible to give an sort of an estimation of what the different costs are?
Yeah, we've found an institute in Germany that supplies the EOF tests, and they it's not that expensive at all, actually. I think about if it was 250 euros or something like that, 2,500 Swedish crowns per sample. I don't know to what degree they sort of sell these tests as a commercial. They do sell it as a commercial test. I think ALS has the top assay for a bit above 6,000 per sample or something like that, and the targeted tests are a bit cheaper, of course. So the top assay, since it's actually 2 analyses that they're doing, is the most expensive one, I would say, but the availability for that one is much better than the EOF.
Then we also have a question regarding these 6,2-FTOH, the telomeric alcohols that break down to PFAS substances, regarding testing for them. Do you have any experience with that? And there is a great interest regarding those substances as well. Are they as easy to test or not?
Well, they are they're the fluorotelomere alcohols, and they're usually you need to, if you want low detection limits, you probably need to go to a GC-MS method, and that's why they're not routinely measured by all the labs, I would say. There are several labs that also provide testing for that, but mostly university labs, and we do as well have methods for the volatile ones. I'm not certain that to what degree the other commercial labs test for these. So there you'd have to go to the websites to see if they provide testing, or get in touch with them if you want a price, or get in touch with us if you want a price from us for testing that. It's a bit tricky with since they're volatile, you need to be careful when evaporating samples and stuff like that, that you don't have losses. But of course, for those, there are internal standards that are isotopically labeled, so you would account for losses using those.
Yeah. And we also have a question regarding there is a great push to regulate PFAS as a family of substances. And if we look at that from the testing limitations, as you said, there are so many different, and it's hard to get a test set up that captures all of the different types. How do you think that will it be possible to regulate PFAS as a class, given these limitations for the tests? What do you think about that?
I think it would be difficult to really keep a track of that they're not there, and also the non-target methods are generally less sensitive than the target methods. So the suspect target and the non-target may not provide you with low enough detection limits to sort of reach what people want to have as limits, or government wants to have it as limits. But I think that there's a great big push now, and it's been present in the EU Green Deal, to push for better and wider testing for PFASs. So I think in a few years' time, I think we will have the tools to look at 100 or 150 PFASs or something like that, and then I think we will be more efficient in the way of actually getting a limitation on PFASs. But many things are probably up to companies actually saying, no, we won't include PFAS compounds. We want to make sure that they're not present.
I think we're almost out of time, but I had one question as well. You said there was a lack of reference material, for example, for the target specific testing. Is that something that you think that that will be solved in the coming years, or will that be a problem? I mean, in combination with the regulation question.
It will be a problem, definitely. It will slowly advance. and we have to, as a lab, cut corners sometimes.
Yep. And we actually had one question in the chat as well. Can all types of samples be tested by TOP and EOF methods, or are these made mainly for water and soil samples?
Well, the example that I showed with the cosmetic products, there it was cosmetic products, so like creams and things like that. So in a sense, any PFAS that can be extracted from a sample will be able to be determined by the test. But you have to be, like, ski waxes they're not easy to analyze, I can tell you that. So you need to have very good extraction methods, and sometimes the standard methods won't really work, but that's for the future to decide, sort of. But anything you can extract, you can test.
Great. Thank you very much, Gunnar. That was very interesting. I think that we are out of questions and out of time as well. I would like to thank you all for joining the webinar. If you have any further questions for me or for Josefin or Gunnar, please contact us. We will make the slides available, and we have recorded the webinar, so we will make that available as well. So thank you very much for today, and have a great rest of the day. Thank you.
Thank you.
Thank you.